Hey you guys, it's Mr. Pincher again. Welcome back to part 2 of our lecture on chapter 4, which is on the continuous time Fourier transform. In this part of the lecture, we'll look at the continuous time Fourier transform for periodic signals. Recall in the last lecture, part 1, we dealt with aperiodic signals, meaning signals that don't repeat themselves. In this part, we're going to deal with periodic signals, and also at the end of this part, we will look at some of the properties of the continuous time Fourier transform. So how do we figure out or derive the Fourier transform for a periodic signal? Well, the way to do it, the strategy here, and this is, there can be a little bit of math involved here, but we sort of use what we learned back in chapter 3 on Fourier series. Remember that a periodic signal, x of t, can be represented as a Fourier series. And this is the complex exponential Fourier series that we used throughout chapter 3. So the idea here is that our signal, which is periodic, x of t, is represented as a sum of a bunch of terms. And each one of the terms looks like a sub k, which is just a Fourier coefficient. And remember, those Fourier coefficients can be determined using this integral here. And that Fourier coefficient is multiplied by a complex exponential, e to the jk omega naught t. Omega naught, remember, is what's called the fundamental frequency of the signal, where t, uppercase T here, is the fundamental period of the signal. So these frequencies up here, k times omega naught, those are harmonic frequencies. So basically, this is again a quick review of chapter 3. A periodic signal can be expressed as a sum of harmonic frequency components of that signal. So the way to proceed here is, this is an infinite sum with all these terms. What we're going to do is basically just find the Fourier transform term by term. So if we just look at, what's inside this summation symbol here, it's shown right here. It's a sub k times e to the jk omega naught t, and we want to find the Fourier transform of that. So that's what this notation here is. F here is for the Fourier transform. So how do we do that? Well, here's the Fourier transform integral, which we learned in part 1 of this video. So I'm just going to take all of this stuff here and substitute it in for x of t in our Fourier transform integral, and we get this expression here. And now we can combine these two exponents together because they're both exponential functions. So we can add those two exponents and we get this form here. And by the way, the Fourier coefficient a sub k, that comes out in front because it's just a constant. So we have this integral over all time of e to the j times quantity k omega naught minus omega times t. What do we do with this? Well, here we can use what we learned in part 1 of this video. Remember this expression here. It's kind of a, odd looking expression, but it's a way to represent a delta function as a Fourier transform integral here. And so by just doing, making the appropriate changes in variables here, remember y, y naught, and x are what they call dummy variables here. We can call them whatever we want. So let's rename y as k omega naught. Let's rename y naught as omega, and we'll do the same thing here on the right side. And let's change x to t. And when we do that, we have basically dressed up this result up here to look like this, which is exactly what we're looking for here. So with this in mind, we can replace this integral with 2 pi times a delta function, and the argument of the delta function is k omega naught minus omega. So that's what I've done in this step here. And then we can also use one of the properties of a delta function is if you switch the terms inside the argument of a delta function, it's still the same delta function. Okay, in other words, the delta function of x is the same as the delta function of minus x. It's just one of the properties of delta functions. So we end up with, this is the Fourier transform of each one of these infinite number of terms up here. It looks like this. It's 2 pi times the Fourier series coefficient, a sub k, and it's multiplied by a delta function that is sitting in frequency at k omega naught. Now remember, omega naught is the fundamental frequency of our signal, and k omega naught is the kth harmonic frequency. So what does this thing look like if we were to plot it? Well, it's pretty simple. The spectrum of just this one term here, this is in frequency domain here, is a spike or a delta function, and it's sitting at the harmonic frequency k omega naught. So whatever k is here, if k is 5 here, this would be 5 times omega naught here, and we have a spike, and the weight of this spike, of this delta function, is equal to 2 pi times the Fourier series coefficient, a sub k. Now, of course, we're not done. All we've done so far is find the Fourier transform of just one of those infinite terms, but we need to find, the Fourier transform for all infinite number of them. Well, that's not as bad as it sounds, because what we can do here is we know that the whole signal x of t is just a sum of all these terms. Therefore, the Fourier transform is going to be the sum of all these delta functions. So finally, we end up with our result here. The Fourier transform, big X of j omega, of a periodic function is equal to 2 pi times the sum of all these delta functions in frequency. And each delta function appears at one of the harmonic frequencies, and it's weighted by a sub k, which is the Fourier coefficient. And of course, remember, that's all multiplied by 2 pi out here. Now, we're sort of halfway done. We found the Fourier transform, but we want a synthesis equation as well. There's sort of a hard way and an easy way to do it. If you want to go through the whole derivation of the synthesis equation, you can follow these steps. But basically, it turns out that for a periodic signal, x of t, the synthesis equation just ends up being the Fourier series for x of t. All right, and the proof of that is shown in this intermediate step, which I'll skip for now. So after all of that, we finally can state our Fourier series and transform for a continuous time periodic signal. The synthesis equation is the Fourier series representation of the signal. And remember, those Fourier coefficients a sub k are given by this integral here. This is a review from chapter 3. We went through all that back then. And then the other, probably arguably more important result is that the Fourier transform of this signal is given by this expression here. It's 2 pi times the sum of a bunch of delta functions, one sitting at each harmonic frequency, k omega naught, and they're weighted by the Fourier coefficient, a sub k. So that was obviously a handful and a mouthful. So what does all this mean? Well, what we've shown is that there are 3 sort of related representations of a periodic signal. The most basic one that we're familiar with, of course, is in the time domain. X of t looks something like this. All right, this is just one example. But this is a periodic signal. It repeats itself over and over every period t. So here's t, here's 2t, 3t, etc. All right, now when we go to the frequency domain, the first thing we can do is find all these Fourier coefficients. All right, the a sub k's, and this is basically what we did in chapter 3. So this is nothing new here. And so these Fourier coefficients, let's say they ended up looking something like this. The last step is to basically replace all of these Fourier coefficients with the Fourier transform, and it's actually pretty simple. We just take all of these values and multiply them by 2 pi. And the frequencies where they sit are just multiples of the fundamental frequency. So remember, omega naught is the fundamental frequency of this signal up here. K omega naught is the kth harmonic frequency. So in other words, if we look at this, here's frequency 0, that's this guy right here. We just take whatever value this red dot is right there, we multiply it by 2 pi, turn it into a delta function, and then the next one over, when k is equal to 1, that's 1 times omega naught. The next one over, 2 times omega naught, 3 times omega naught, 4 times omega naught, and so on and so forth. And you can see that these delta functions, they align with these up here. We're just taking their value and multiplying each one by the value of 2 pi. By the way, there's a much simpler way to derive the results that I showed on the last few slides. You can pretty much do this by inspection. This is not shown in your book, but it's kind of a clever little shortcut that I came up with. If you think about the continuous time Fourier series from chapter 3, x of t is the sum of a sub k times e to the j times k omega naught times t. Let's write the continuous time Fourier transform synthesis equation, which is shown here. This is from part 1 of chapter 4, what we did in our last video. So basically the trick here is to make these two expressions equivalent. Now, so what do we have to do? Well, basically what we have to do is we have to take this Fourier transform here and dress it up the right way to make this expression look like this one. And believe it or not, it's not as hard as it might seem. So the first thing we need to do is notice there's no 2 pi or 1 over 2 pi up here, but there's a 1 over 2 pi down here. So x of j omega is going to have to get rid of this 2 pi. So x of j omega is going to have a factor of 2 pi in it. Okay, that will cancel the 1 over 2 pi. The next thing we can do is notice up here there's an a sub k, and here there's none. So that tells us that x of j omega is going to have a factor of the Fourier coefficient, a sub k, in it. Okay, so we're partway there. Now, maybe the more tricky part is that we have to get this integral here to look like this sum up here. And the way to do this is to use a delta function that will force omega to be equal to k omega naught. Because notice here we have an omega, up here we have k omega naught. So if we multiply our result here by a delta function of omega minus k omega naught, that's going to force this omega to be equal to k omega naught. And then the last thing we have to do is just sum over all k, and we get the same result we got on the last slide. All right, so let's now do something that's actually more important than just deriving these results. Let's actually put it to use and look at some applications and examples of the Fourier transform for a periodic signal. So we'll do a few different types here. Let's start with a periodic square wave signal. So remember from chapter 3, we were introduced to the square wave or rectangular wave periodic signal. It looks like this. You can see it has a width of w, and it shows up every period t. So back in chapter 3, we found the Fourier coefficients a sub k for this periodic square wave. So that's going to always be our starting point. We're going to find the Fourier coefficients first, and they're shown, mathematically here. We did this in chapter 3, and they're plotted here. The next thing, all we have to do is take each of these values of a sub k and multiply them by 2 pi. Okay, so and then turn them into delta functions, all right, in frequency. And then, of course, the values down here for k become multiples of omega naught. So we have omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and so on and so forth. When you actually do the math here, and you multiply, for example, this first one here, when you multiply it by 2 pi, you'll end up getting the result of pi here. Oh, and by the way, if you're wondering this result here, all right, so how did that pi come up there? Well, notice for this example here, I forgot to mention this. This is for the case where t, the period, is 2 times w, the width. Remember that the width is the width of the pulse here, and t is the period. So if we have t equals 2w, then what we have out here is w over 2w, which is 1/2. And when we multiply that 1/2 by 2 pi, we end up with a pi here. And you can do the same thing for all of these coefficients. Let's look at another example here. This is one for a cosine signal. So this is going to be one that is very important. It's going to show up quite a bit in the course. So let's let our signal x of t be just a basic cosine function. Cosine of omega naught t looks something like this. Omega naught is obviously the frequency of the cosine function. So the first thing, again, since this is a periodic function, the way to find the Fourier transform is by first finding the Fourier coefficients. And again, we did this back in chapter 3. So this is, why chapter 3 was so important, because a lot of the results from there we're actually using right now in this part of chapter 4. So recall for the cosine function, there were two coefficients. A1 was 1/2 and A of -1 was also 1/2. So all we have to do then to find the Fourier transform is multiply each of these coefficients, the AK's here, multiply them by 2 pi. So 2 pi times 1/2 is just pi. So that gives us the weight of these two delta functions. Now, where are the delta functions sitting? Well, they're sitting at, remember, there's only two Fourier terms here when k is 1 and when k is -1. So that corresponds to 1 times omega naught and -1 times omega naught. That's where those frequency spikes are. All right, so what does this mean? How do we interpret this spectrum? Well, remember, x of j omega, this is the spectrum of the cosine function. All right, so this is what the cosine function looks like in the time domain. This is what it looks like in the frequency domain, and it makes sense because if you think about the cosine of omega naught t, it only has a single frequency, and that frequency is omega naught. And so that is where we see the spectrum. We see the spectrum at omega naught and nowhere else. All right, omega naught, and of course, remember it's always symmetric. There's also a minus omega naught here. But the key thing is that the cosine function, since it's a pure frequency, there's no other frequencies other than omega naught. So we see a spike or a delta function in its spectrum there. This was another example that we did actually back in chapter 3, so we're going to borrow the results from that. This is an impulse train. All right, so we've got a sequence of impulses in time. That's our signal. And back in chapter 3, we found that the Fourier coefficients were all equal to 1 over t, where t is the period. So the Fourier series coefficients look something like this. It's also sort of like an impulse train, and every value is 1 over t. So to get the corresponding Fourier transform, all we do is turn all of these into delta functions, and we multiply this value, 1 over t, we multiply it by 2 pi. So we have the weight of each of these delta functions is now 2 pi over t, and remember they're going to occur at harmonic frequencies. So the harmonic frequencies are, remember the fundamental frequency is given by 2 pi over t, so that's this right here, and then this is twice that and 3 times that, and so on and so forth. Let's now take a look at some of the most important properties of the continuous time Fourier transform. Your textbook lists several other properties that I'm not going to discuss here, but the ones that are the most important to us I will talk about next. So the first thing we're going to do before we look at the properties is adopt sort of a shorthand notation for the Fourier transform pair. And this is kind of reminiscent of what we did in chapter 3. So this notation right here basically tells us that in the time domain, we can have a signal, let's call it x of t, and in the frequency domain, the corresponding signal is its spectrum, or Fourier transform, uppercase x of j omega. So notice this is a function of time over here, and we have a lowercase x. This is a function of frequency here, and it's always represented by the uppercase letter that is over here. So this is, this is a pair, right? This is a signal and Fourier transform pair that are, associated with each other. That's what this arrow means. We can go from here to here, or we can go from here back to here by doing the appropriate calculations. So the first property is just linearity. If, some function x of t gives us big X of j omega, and likewise some other function y of t gives us big Y of j omega, then if we add x and y together and weight them by C1 and C2, then by linearity, the output, or the Fourier transform of that signal will also be weighted by those same coefficients and added together. Time shifting is a property, and we can derive the time shifting property as follows. We've got let's use our synthesis equation here. All right, for this is the Fourier transform embedded inside this integral here, and this is x of t over here on the left. So what happens if we delay x of t by some amount t naught? So right, this is a time shift, okay, or a delay by t naught. So all we have to do is wherever we see a t over here, we replace it with t minus t naught. Now what we can do is a little trick here. We can take this j omega and distribute it inside the parentheses and break this exponential function into two exponentials, e to the minus j omega t naught multiplied by e to the j omega t. All right, that's the same thing as this thing written together like this. And I'm going to group this together and put brackets around this and leave the e to the j omega t d omega over here. So if I compare what's in this blue box with our synthesis equation up here, this tells us that the Fourier transform x of j omega here has been replaced with all this stuff inside the square brackets here. Okay, then they're identical to each other. So what that tells us is if x of t has the Fourier transform big X of j omega, then x of t minus t naught has a Fourier transform equal to x of j omega multiplied by this phase factor, e to the minus j omega t naught. So, kind of the meaning of this all is that time shifting changes the phase of the Fourier transform, but leaves the magnitude unchanged. Because remember, this complex exponential function here has a magnitude of exactly 1, all right? But obviously it has different phase, all right? It doesn't have a phase of 0. It has a phase of minus omega times t naught. So this tells us that the frequency components are shifted in phase due to a time shift. So one way to kind of try to visualize this, because I realize a lot of this is a bit abstract, if we start out with a red, this is a sine function here that I drew, for example, all right? This is sine of omega t. And if we do a phase shift, so that's x of t, right, in red, then x of t minus t naught, we're just going to shift this thing over to the right because it's delayed by t naught. And so what happens here is we have sine of omega times t minus t naught. Well, let's distribute the omega in there. So we get omega t minus omega t naught. So this term, this last term here, represents the phase shift, delta phi, if you want to call it that. These are both obviously still sine waves or sine functions, but they have been shifted not only in time, but you can think in frequency domain, they've been shifted in phase. And so that's what the time shifting property is telling us. Let's look at an example here of time shifting. So let's suppose we're given the following signal. X of t is equal to 5 times e to the minus 2t times u of t. We're asked to find the Fourier transform of the delayed signal x of t minus 3. So how do we approach this? Well, what we're going to do is let's find the Fourier transform of the original signal first. So that's easy enough. We can use results from part 1 of our video lecture in this chapter 4. And this is a simple basic exponential function. So remember this result, we did a whole bunch of these in the last video. And when x of t is e to the minus at, we have the Fourier transform is 1 over a plus j omega. So just by inspection, I can see that a is 2, so that's the 2 down here. And this 5 out in front, I'm just going to stick that up at the top like this. All right, so this is the Fourier transform for x of t. Now, we want to find the Fourier transform of x of t minus 3. Well, all we have to do is apply the time shift property. If we have a delay of t naught, then we just take this result and simply multiply it by e to the minus j omega t naught, and t naught is obviously 3 by looking at this and comparing it to this. So we have a factor of e to the minus j 3 omega, that's our phase shift, and we multiply that by this result here to get our final answer, which is 5 times e to the minus j 3 omega over 2 plus j omega. Here's another example using the time shifting property. This one we're going to work backwards. Suppose that we are given the following Fourier transform. Big Y of j omega is equal to 4 times e to the minus 2, e to the minus j 2 omega divided by 3 plus j omega. And our goal is to find the signal, little y of t, that corresponds to this Fourier transform. So obviously we need to do a reverse or inverse Fourier transform here. So how do we tackle this thing here? Well, when we see this term here, this indicates a phase shift, because remember that looks just like this term out in front here. So what I'm going to do is I'm going to take this 4, in fact I'll take the whole numerator and stick it out in front of what's left is 1 over 3 plus j omega. So this e to the minus j2 omega represents a delay of 2. Remember this up here, if you let t naught equal 2, we get this exact same term. So all we have to do is find the signal that corresponds with 1 over 3 plus j omega. Well, that's easy enough. We just use our result from part 1. We can see that a is equal to 3. So this must be equal to e to the negative 3t times a step function of u of t. And then we need to do two things. We need to multiply it by 4. So we'll put the 4 out in front. And we need to delay everything by 2. In other words, wherever we see a t, here's one here, and here's one here, we replace that t with t minus 2. So here's our final function, y of t, for this Fourier transform here. Here's an example that uses both linearity and time shifting. So suppose that we're given a signal y of t that looks like this. So it's sort of a rectangular pulse, and but it's not centered around 0. Notice it starts here at 4 seconds and it ends up here at 8 seconds, and it has a value of 10. So this is a scaled and shifted version of this rectangular pulse right here. All right, if we compare these two here, all right, we notice, there's two things different. First of all, this one has a value of 1, and this one has a value of 10. So obviously, we just have a factor of 10. But more importantly, this one up here has been delayed by 6 seconds from this one. This one's centered at 0. This one here is centered at 6 seconds. So we're going to have to implement a delay, a time delay, into our result, as well as a factor of 10. So, this square pulse right here, we looked at this previously. This is what we did in part 1 of chapter 4 video. And this was the result right here. Okay, so I'm not going to go through that again. And what we notice here is that the t is the half width. So remember, if this is centered at 6, the half width is 2 seconds. So we can replace this t here with a 2. And then finally, we need to multiply by 10 and delay by 6. So this x of j omega, which corresponds to this guy here, we have to multiply it by 10 to make this 1 turn into a 10. And we have to multiply the whole thing by e to the minus j omega 6, because that is the time shift of 6 seconds to move it from here at 0 over to here at 6. So when we multiply 10 times e to the minus j omega 6 times all of this here, we end up with this form right here. And by itself, it's hard to really tell what that looks like. So we could go ahead and plot the magnitude and phase of this, but I did not do that in this problem. I'm just going to leave it in this form shown here. There's another property that we're going to use later in the course called frequency shifting. And this is somewhat similar to time shifting. What we're going to do, though, is we're going to work with instead of working with the signal or the synthesis equation, we're going to work with the Fourier transform spectrum integral right here. And so this is the Fourier transform integral, which we learned in part 1. And we're going to replace omega with omega minus omega naught, which this represents a shift in frequency. All right, so we're shifting it up. We're shifting the whole transform up to a higher frequency. So what does that do to the right side? Well, wherever we see an omega over here, we have to replace it with omega minus omega naught, and then we can split up these exponential functions just like we did for the time shifting property, break them apart and lump them together like this, and when we compare everything in the blue box with the original, we see that x of t up here is replaced with x of t multiplied times e to the j omega naught t down here. So this tells us that when we have a frequency shift over here in the frequency domain of omega naught, in the time domain we have the same function x of t, but it's multiplied by e to the j omega naught t. And you know, once again we kind of see this duality or dual property of between time and frequency. And in this case, it's time and frequency shifting. So you know, we saw that a shift in time means we have a phase factor out here in front of the Fourier transform. And conversely, when we have a shift in frequency over here on the right, we have a phase factor in front of the time signal over here. Let's now take a look at something called the differentiation property of the Fourier transform. And this is arguably one of the most important properties of the Fourier transform because it's going to allow us to replace derivatives with just basically an algebraic factor. In other words, we'll be able to remove calculus from a differential equation and just turn it into an algebraic expression. And so this is a really important property that we're going to exploit over and over, especially when we get to solving differential equations later in this chapter. So the way to derive this is actually pretty simple. We'll start with the Fourier transform synthesis equation here. And what we're going to do here is we want to take the derivative of the signal x of t. So we take the time derivative, so we have dx dt. And of course, if we do that on the left side, we have to take the time derivative of the right side. So if we look over here on the right, the only thing that has time in it is this exponential function, e to the j omega t. So when we take the derivative of that, we get a factor of j omega that comes out in front. And so I'm going to put that j omega in front of the Fourier transform, x of j omega. And then if we compare these, we see that everything here, up here, looks the same as down here. What this tells us is that the stuff in the square brackets here has to be the Fourier transform of dx dt. So if that wasn't super clear, don't worry about it. Here's the important thing. The differentiation property says the following. If we have some signal x, little x of t, that has a Fourier transform, big X of j omega, then the derivative of x of t, the time derivative of x of t, has the same Fourier transform, but we've picked up a factor of j omega, right? That's this factor here that we picked up when we took the derivative of e to the j omega t. So derivatives in the time domain are replaced by a simple factor of j omega in the frequency domain. All right, so instead of working in the time domain over here with derivatives, we're going to work in the frequency domain, and there's no calculus here. All right, this is just a factor of j omega. So here's an exercise for you to try. What would the result be for the second derivative, the second time derivative of x of t, or for example, the third time derivative of x of t? See if you can kind of go through the same step here that I did and see if you can come up with a result for both of these. So here's the solution here. Basically, each time you take a derivative, you pick up a factor of j omega. So if you have a first derivative of x, you end up with j omega times the Fourier transform, big X. If you have a second derivative of x with respect to time, you pick up a factor of j omega squared times the Fourier transform, big X. And this just repeats. A third derivative would lead to j omega cubed in front of x, and so forth. So again, this at first glance, it may not be super obvious the importance of this, but we will use this property later in this chapter, and we will figure out a way to solve differential equations without using any calculus at all, without having to deal with these derivatives over here. We're going to just use all of these expressions here, which are just simple algebraic expressions. And so based on this, we'll be able to solve differential equations virtually by inspection. So that's sort of looking ahead to a later part of this video. But that's it for now in part 2, and I will see you shortly for part 3. Until then, take care and goodbye.